Lecture 7 is delving into pump system analysis. We've been talking about pump head curves. Now we're actually going to get down to the point of how do you select a particular pump. So we're going to get into something called the system head curves today, and we're going to talk about how to compute those. And then as we have that system head curve, and we'll couple it with the pump manufacturer's curve or the pump head curve, we'll get the pump operating point. So if we have a system head curve, we've already been talking about the pump head curves, and that's shown here in this graphic right here. The system head curve has to be determined, which is not going to be a static thing, because as the flow changes in the system, the head that will be needed from the pump will change as well. And so we're going to be looking at drawing some sort of system head curve that will be, from the system standpoint, writing an energy equation, including the pump in there, from one location through the pump to another location to come up with the system head curve. This system head curve, when it intersects with these various pump curves, those become pump operating points. So if I selected the 27-inch diameter pump, this would operate at about, let's see, it's about a 5,800 GPM capacity with a head of about 175 feet, and so on and so forth as you move up through. Now, let's look at this. If the pump is not operating at all, there's no flow in there, there's a certain static head that it has to overcome. And so there's absolutely no flow that's going to be initiated until I turn this pump on, and then we can assume that as the discharge increases, the pump head has to increase because of why? Because of friction and the other minor losses. And so this graph here has a form that's a function of V squared, because remember, the head loss due to friction is F L over D V squared over 2G. So there is, as the discharge increases, the velocity is going to increase, and the minor losses are what? The sum of the K's, V squared over 2G. So the combination, again, there's that V squared. This curve is going to vary with the square of the velocity. So there's the pump with positive lift as we define it, and that's where you're going from this reservoir to this one. You have to overcome that static head. If I've got a reservoir that is above where, so if I'm going, the flow is going this direction here, you notice that before the pump's ever turned on, we can have a discharge. And so once we get the pump turned on, we end up having pump head added in. And the only reason why we'd have a pump in a situation like this is to be able to provide more flow than the gravity pipe flow would be able to impart. If I've got two pumps with different discharge heads, you can see that as I'm going from this lower location and I first start pumping, and I'm going to pump into this lower reservoir, and then as I get into the upper reservoir, once I get enough head induced, I can actually pump into the upper one. So I could write a system curve for this lower reservoir, for the lower to the, let's number these, reservoir 1 to 2, and that would be this curve. And then from 1 to 3, that would be this curve. Now, if I superimpose these on each other, this new static head, or not static head, but the system curve becomes this to here. So this is no longer part of it. This is just by superposition. This allows me to place in a new system head curve. If I've got a situation where I'm pumping and the reservoir elevation in the upper one changes to, enough that we can feel it from the head we're pumping against, you can see that we've got two different system curves, one for the minimum amount of lift, one for the maximum amount of lift. So as we look at how do we write a system head capacity curve, so the first thing we're going to do is we're going to write the energy equation from a point of known information upstream of the pump, through the pump to another point of known information that's downstream of the pump. And we're going to isolate the energy equation for H sub P. So here is my energy equation that I would write for this particular application. And then I'm going to isolate and solve. I'm going to move everything to one side except for the H sub P, and I'm going to plug in various values of Q to give myself values of HP. And that way I can come up with an HP versus Q curve. That is the system curve. It's relatively, well, it's a fairly straightforward concept. Saying that it's simple would give a false sense of security, because I know students sometimes struggle with this, but it is not that difficult as long as you follow the first principles, being writing that energy curve, energy equation from one location to the other through the pump, making sure that you're including the pump, the friction losses, and the minor losses. Now, where people get confused is this is different than when we're looking for net positive suction head available problems. There we write the energy equation from like section 1 to the eye of the pump, point A. That is not the problem we're solving here with a system head curve. We are not looking for the net positive suction head available. Although that's part of the design process, that is not what we're looking for. All right, so if we look at this, we've got a problem here where we've got two different types of material in terms of pipes. We've got a 12-inch pipe here on the upstream end, and there's 100 feet of it. Then we've got our pump, and then we've got 1,500 foot of 10-inch pipe. Now the problem is simplified because we're giving you the friction factor, and I'm going to work an example problem that's not going to have the friction factor in there, and you're going to have, and it's basically because the friction factor is a function of both the relative roughness and the Reynolds number. Here we're assuming it's just constant, but you can get problems. In the one I'm going to work an example for you in a recording for this lecture series on lecture 7. I'm not going to assume a constant value of friction, and that way I'm going to let the friction vary, and I'm going to show you how to work that problem. As we go through here, we write the various losses in terms of the particular types of pipe you've got. And so we have to break this down where we've got the friction loss, do the 12-inch pipe, which that's the first 100 feet. You'll notice L12 would be 100 here. The friction factor is going to be the same whether it's a 12-inch or a 10-inch. This has got actually, I think, a misprint here. That should be 10 inches for that instead of 12 inches. But because of the same, it doesn't matter. And so we can enter in all these values for the F, the L, and the D, and the A, and you can come up, because we've pulled Q squared through, right? We can write this equation out, solve for these things here. We've got the entrance and the check valve K values. We've got the, this will be for the 12-inch. And then for the 10-inch, we've got a couple of gate valves, and we've got an exit loss. And so we plug those in. If we do all that, we come up, this is our system head curve. Now remember, we've got this in terms of velocity here, but we know that the velocity is nothing more than Q over A. So that's how we end up getting the Q squared pulled through on this equation. So you need to look at that. If it's a little confusing to you, you need to kind of work through this problem, starting from this energy equation from here to there, and then make sure you understand how I get to this point right here where the Q is pulled through. And so we've got the various, we have to break that, because we have two different pipes, we have to break our losses for friction down into this particular section and this section. So they've shown it as two different ones, but the Q squared is common to all these terms. So it's pulled through the bracket. And then we've got the minor losses on the 12-inch pipe section, and we've got the minor losses on the 10-inch pipe section. So make sure you can do that and end up getting this as my value for the system head curve. That'll be something really good for you to work through and make sure the numbers come out for you. All right, so really quickly, to kind of put a wrapper onto this, I want to go through a few slides here, look at different scenarios. And so if I've got a head curve here, a system head curve on this particular operation, I've got a pump head capacity curve. That intersection point is where we're going to have the pump operating point. And if this is my efficiency curve, you can see my maximum efficiency would be right here. My pump is operating right here, which is not too far off the maximum efficiency. Might not be too bad of a selection. So let's look at some more different kinds of things here. Again, if I threw this up to you, this was two different pumps, what would this tell you? This is a pump, two pumps operating in parallel or in series. Because we're adding no more head, I'm going to say these are acting in parallel because it's adding discharge but not additional head. We've already talked about this maximum lift stuff that was on a previous slide. Let's say that I had two different pumps like that. So I had two different pump curves. One is just with one pump operating, one is with the second pump operating. These are again in parallel. And then I've got this maximum static lift here that's got a minimum and, or not a static lift, but a minimum lift and a maximum lift. So I've got two different system curves. I've got two different pump curves. There's actually 4 points that I could have as my operating points for that particular pump system. And then if I throw on top of that, I get some variable speed pumps where I've got 3 single speed pumps of different sizes. And then I operate those in parallel. You can see that I've got to modify my pump operating curve such that I have all these different potential operating points for those 3 particular types of pumps. Now, again, I'm not expecting you to master this. I'm just trying to show you the kind of the differences that you would have with different types of combination of pumps. So it can get really complicated with various pumps. And this takes a bit to analyze and make sure you're doing the design correctly. But again, we're only going to worry about doing a single pump in our design. This is a single pump with variable speed. And again, if the pump is operating speed of 85% of its maximum all the way up to 100%. But you can see at the 90, 95, you've got different points that this pump could be operating at in terms of its flow and its head. Again, if you've got aging pipes, here's our pump curve, and the pipes get older, and you can see as they get older, their roughness changes. And so we go from when it's a new pipe having this very high discharge, lower head, to when it's a lot rougher with scale buildup and things like that, to where we've got a higher head with a lower discharge that were required for this operating range.